Welcome to this comprehensive tutorial on Pytorch loss functions. Today we're going to demystify 4 commonly confused loss functions that beginners often struggle with. These are torch.nn.functional.binary CrossEntropy, also known as BCE, torch.nn.functional.binary CrossEntropy with logits, or BCEL, torch.nn.functional.CrossEntropy, and torch.nn.functional.NLL loss. The confusion typically arises because BCE and BCEL both handle binary classification but have different input requirements, while CrossEntropy and NLL both work for multi-class tasks, but CrossEntropy actually includes log softmax internally. We'll explore why these different versions exist, particularly focusing on the critical differences between probabilities, logits, and log probabilities, and why numerical stability makes BCEL preferable to BCE plus sigmoid. Let me show you a visual overview of the loss functions architecture. This diagram illustrates how these 4 loss functions relate to each other and what inputs they expect. As you can see, BCE needs probabilities while BCEL takes raw logits, and CrossEntropy combines log softmax with NLL loss internally. Let's start by importing the necessary libraries for our tutorial. We'll use Pytorch for the loss functions, NumPy for numerical operations, Matplotlib for visualizations, and Seaborn to make our plots look nicer. I'm also setting a random seed to ensure our results are reproducible. Here's a quick reference guide showing the input requirements for each loss function. This visual summary will help you remember what each function expects. Notice how BCE requires probabilities between 0 and 1, BCEL works with raw logits, NLL needs log probabilities, and CrossEntropy also takes raw logits. Now let's dive into part 1, where we'll explore binary classification and compare BCE versus BCEL. We'll start with the simplest possible example to make the concepts crystal clear. Let me demonstrate the simplest binary classification example. I'm creating 4 samples with raw model outputs, which we call logits. These are values like 2, -1.5, 0.5, and -0.3, representing the raw output from a neural network before any activation function. Our targets are binary labels, either 0 or 1, representing 2 classes. Now watch what happens when we use BCE. It requires probabilities, so we must first apply the sigmoid function to convert our logits into values between 0 and 1. Then we can calculate the BCE loss. On the other hand, BCEL takes the logits directly and applies sigmoid internally, which is why it's called binary cross-entropy with logits. Let me verify that both approaches give us the same loss value. Perfect. As you can see, the logits are our raw model outputs, and the targets are simple binary values. After applying sigmoid, our logits become probabilities ranging from about 0.18 to 0.88. Both BCE with sigmoid applied and BCEL give us exactly the same loss value of 0.3392, confirming they're mathematically equivalent. The checkmark shows that BCE and BCEL indeed produce the same loss value when used correctly. Now let's explore why BCEL is actually preferred over BCE, and it all comes down to numerical stability. This is a critical concept that can prevent bugs in production systems. Let me demonstrate the numerical stability issues with extreme values. I'll use logits of 50 and -50 to show what can go wrong. When we apply sigmoid to these extreme values, watch what happens. Sigmoid of 50 becomes exactly 1, and sigmoid of -50 becomes effectively 0. This creates a problem for BCE because it needs to compute the logarithm of these probabilities. Log of 0 is undefined, and log of 1 is 0, which can cause numerical instabilities. BCEL, however, handles these extreme values gracefully by using a numerically stable formulation that combines sigmoid and cross-entropy in a single step. You can see that with extreme logits, the sigmoid function saturates, giving us 1 for the positive extreme and essentially 0 for the negative extreme. BCEL handles this gracefully and gives us a loss of 0. The manual BCE calculation requires clamping to avoid taking the log of exactly 0 or 1. This is why BCEL is preferred. It doesn't require any workarounds for numerical stability. Let's move on to part 2. where we'll explore multi-class classification and understand the relationship between cross-entropy and NLL loss. Here's the simplest multi-class classification example. We have 4 samples and 5 possible classes. The raw model output, our logits, has shape 4 by 5, meaning 4 samples with 5 logit values each. Notice that our targets are just class indices from 0 to 4, not one-hot encoded vectors. CrossEntropy takes these logits directly and internally applies log softmax before computing the negative log likelihood. If we want to use NLL loss instead, we need to manually apply log softmax first to get log probabilities, then pass those to NLL. Let me show you that both approaches give the same result. Great! Our logits have the expected shape of 4 samples by 5 classes. The targets are simple class indices 0, 2, 1, and 4. CrossEntropy gives us a loss of 1.3351, and when we manually apply log softmax and then use NLL, we get exactly the same loss value. This confirms that CrossEntropy equals log softmax plus NLL. Now, let's break down the mathematical relationship step by step to really understand what's happening inside CrossEntropy. Let me demonstrate the mathematical relationship step by step with a simple example. We have 2 samples and 3 classes. First, we apply softmax to convert logits to probabilities that sum to 1. Then, we take the logarithm of these probabilities. Next, for each sample, we select the log probability corresponding to the target class. Finally, we take the negative mean of these selected log probabilities to get our loss. This is exactly what CrossEntropy does internally in one efficient operation. Perfect demonstration. Starting with our logits, the softmax gives us probabilities that sum to 1 for each sample. Taking the log gives us log probabilities, all negative values. We then select the log probability for each target class, which gives us negative 0.417 for class 0 and negative 0.197 for class 1. The negative mean of these values gives us our final loss of 0.3069, which matches exactly what CrossEntropy computes. This manual calculation confirms our understanding of the mathematics. Let's visualize how softmax transforms logits into probabilities to build more intuition about multi-class classification. I'm creating a visualization to show how softmax transforms logits to probabilities. For 3 different samples, you'll see the raw logits on the left, which can be any real values, positive or negative. On the right, you'll see how softmax transforms these into probabilities that always sum to 1. This transformation ensures that we get a valid probability distribution over our classes. Beautiful visualization. On the left, you can see the raw logits for each sample, with both positive and negative values. On the right, after applying softmax, all values are transformed into probabilities between 0 and 1. Notice how each sample's probabilities sum to exactly 1, as indicated by the annotation in each probability plot. This is the key property of softmax. It creates a valid probability distribution regardless of the input logit values. Now let's look at part 3, where we'll directly compare binary versus multi-class classification. This diagram shows the key architectural differences between the 2 approaches. Let me show you a side-by-side comparison of binary and multi-class classification to highlight the differences. Here's a direct comparison of binary and multi-class classification. For binary classification, like distinguishing cats from dogs, we use a single output neuron and binary targets of 0 or 1. The model output shape is batch size by 1. For multi-class classification with 3 classes, say cat, dog, and bird, we need 3 output neurons, 1 for each class. The targets are class indices from 0 to 2, and the model output shape is batch size by 3. This is a fundamental architectural difference you need to understand when designing neural networks. Excellent comparison. For binary classification, we have 8 samples with single outputs and binary targets showing a mix of cats and dogs. The BCEL loss is 0.6841. For multi-class with 3 classes, we have 8 samples with 3 outputs each, and targets showing indices for dog, cat, and bird. The CrossEntropy loss is 1.5479. The key takeaway is that binary uses 1 output with sigmoid, while multi-class uses C outputs with softmax. In part 4, Let's explore common mistakes that developers make with these loss functions and how to fix them. Let me show you two common mistakes. First, passing logits directly to BCE, which expects probabilities. This will cause an error because BCE checks that all inputs are between 0 and 1. The fix is to either apply sigmoid first or use BCEL. Second, using one-hot encoded targets with CrossEntropy. CrossEntropy expects class indices, not one-hot vectors. However, CrossEntropy can also work with soft targets, which are probability distributions, useful for knowledge distillation. Perfect demonstration of common pitfalls. The first mistake shows that BCE will error when given logits outside the 0 to 1 range. The correct approaches both give a loss of 0.3048. The second mistake would error with one-hot targets, but works correctly with class indices, giving a loss of 1.0517. Interestingly, CrossEntropy also accepts soft targets for advanced use cases like distillation, giving a loss of 1.2465. Let's move to part 5 and see these loss functions in action with a practical classification task. I'm creating a synthetic dataset for demonstration. We'll generate 100 training samples and 20 test samples with 10 features and 3 classes. This simulates a real-world multi-class classification problem where we need to distinguish between 3 different categories based on 10 input features. Our dataset is ready. We have 100 training samples with 10 features each, targeting 3 classes. The class distribution is fairly balanced with 29, 36, and 35 samples in each class respectively. This is a good starting point for our classification task. Now I'll create a simple linear classifier and train it using both CrossEntropy and NLL loss to show they achieve similar performance. The model just has a single linear layer that maps our 10 input features to 3 output logits. I'll train each version for 50 epochs using the Atom optimizer. Notice that for CrossEntropy, we pass logits directly, while for NLL, we need to apply log softmax first. Excellent, both training approaches converged successfully. The final CrossEntropy loss is 0.5647, and the final NLL loss is 0.5475. These values are very close, confirming that both methods achieve similar performance. The checkmark indicates that both CrossEntropy and log softmax plus NLL are equivalent approaches to training. Let me visualize the training curves and test set performance for both models to show they behave similarly. The visualizations show great results. On the left, the training curves for CrossEntropy and NLL follow nearly identical paths, both decreasing smoothly over 50 epochs. On the right, both models achieve 55% test accuracy, demonstrating that the choice between CrossEntropy and NLL doesn't affect model performance. It's purely about convenience and numerical stability. In Part 6, let's explore advanced topics, specifically how to handle imbalanced datasets using class weights. Let me demonstrate handling imbalanced datasets. I'll create a dataset where class 0 is rare at 10%, class 1 is 30%, and class 2 is the majority at 60%. To balance the loss contribution, we calculate inverse frequency weights. These weights give more importance to rare classes. For binary classification, we can use the pose weight parameter in BCEL to upweight the positive class when it's underrepresented. Great demonstration of handling imbalance. Our dataset has a realistic imbalance distribution with class 0 at 10.3%, class 1 at 30.4%, and class 2 at 59.3%. The calculated class weights are 1.98, 0.67, and 0.34, giving more weight to the rare class. The weighted loss of 1.3795 helps balance the contribution compared to the unweighted loss of 1.3951. For binary classification, with only 19.3% positive samples, using a pose weight of 4.18 increases the weighted BCEL to 1.3273 from the unweighted 0.8194, helping the model pay more attention to the minority class. Let me summarize the best practices and provide a quick decision guide. The table shows when to use each loss function. For binary classification, use BCEL because it's numerically stable and takes logits directly. For multi-class, use CrossEntropy as it's an all-in-one solution. For multi-label where each label is independent, use BCEL. The common pitfalls include never applying softmax before CrossEntropy or sigmoid before BCEL, using class indices not one hot for CrossEntropy, checking value ranges, and preferring the WithLogits versions for numerical stability. The key takeaways are that BCEL equals BCE plus sigmoid, but more stable, CrossEntropy equals log softmax plus NLL, but more convenient, input format is crucial, numerical stability matters, and shape requirements differ between binary and multi-class. I'm creating a visual decision flowchart to help you choose the right loss function for your task. This decision tree will guide you through the key questions to ask when selecting a loss function. This decision tree provides a clear path to choosing the right loss function. Starting from your classification task, you first determine if it's binary or multi-class. For binary tasks, consider if you need numerical stability, then BCEL is recommended, shown in green. For multi-class tasks, if you need log probabilities separately, use NLL, otherwise CrossEntropy is the recommended choice. The green boxes indicate recommended options, while yellow shows alternatives. Finally, let me provide a quick reference function that recommends the appropriate loss function based on your requirements. This function takes into account the task type, input format, whether it's multi-label, and if you need probabilities for other purposes. Let me test it with several common scenarios. Perfect. Our recommendation function correctly identifies the best loss function for each scenario. For binary classification with logits, it recommends BCEL. For binary with probabilities, it suggests BCE. For multi-class with logits, CrossEntropy is recommended. For multi-class with log probabilities, NLL is the choice. And for multi-label binary classification, BCEL is again recommended. This completes our comprehensive tutorial on Pytorch loss functions.